trying to go to the Paris Observatory, which is one of the most prestigious and most active centers of astroparticle research in the world. So the idea is that we're going to try and link up with George Smoot, a Nobel Prize winner from 2006, and find out what he has to say about astroparticle physics. So George,
well, I lost my helper, but we can go ahead now. I just wanted you to notice that I am in one of the most historic places in Paris. And you have this picture of Louis XIV right behind me with his cape, but also the famous scientist.
George, I've had the great pleasure of going to the Paris Observatory. You're absolutely right. It's a wonderful place.
It looks absolutely fantastic, yes. So tell me, George, have you been able to speak to Frascati?
I haven't heard from them yet. We were doing an event here, which was a local European Researchers' Night up until just a little while ago. And so I actually hadn't tried. So we hooked up just to go directly to CERN. And so hopefully that'll be sufficient connection. Otherwise, maybe Frederick knows how to make the next connection.
That's okay, George, don't worry. Maybe we can ask you a few questions from CERN while, and if Frascati join in, that's fine. George, you got the Nobel Prize
I
for...
hope so.
You got...
Paula supposedly has my videos and some view graphs, if she checked her mail lately.
Okay. You got the Nobel Prize. Could you tell us, for those of us who are not following this field, what did you get the Nobel Prize for?
All right. Well, I shared the Nobel Prize with my colleague, and we got it for first showing that what we call the cosmic microwave background is the relic radiation left over from the beginning of the universe. And then the second part was the part done by the team that I led, which was to make a map of the embryo universe using that light, using the very first light in the universe, using it as a source to illuminate what was going on in the early universe, just like you take a picture of the sun and you can see the sun is round and sunspots and so forth. We're seeing the very same things at the beginning of the universe.
So how did that help us understand the universe better?
All right, so in our view of the universe, we live now in a universe which is expanding, and it's been expanding for almost 14 billion years, so we're quite far along. And what we can do is, from this radiation, we can see back directly to a time when the universe was quite a lot younger, sort of compared to your age, back to 12 hours after conception. But by mapping it carefully, we can see the sound waves that came from the early universe, and we can actually see back to the very early part of the time. If you look at what goes on over in that epoch, we can see back to when the universe was 1,000 times smaller, right? So we can, with the sound waves, we can look back at even bigger factor than that. So we can look back to the time when everything we can see in all directions now, which includes 100 million galaxies, so 14 billion light years in every direction. We can now look back to a time when that was very small, and we think extrapolated back to a time when it was smaller than an atom, so that we were getting to the very small, the kind of things that are done in particle physics. And we have this direct tie, and I sent this picture of the thing we call the Ouroboros, the snake that's swallowing its tail. And in this, there's the famous quote I did from Blaise Pascal, that man is suspended between the infinitely small and infinitely large. And in this picture, you see that humans are roughly on a scale that's halfway geometrically between the biggest scale we can see in the universe and the smallest scale we can see with particle physics. And it's quite amazing to think about that, but it's also quite amazing to think that when we draw this picture with the snake swallowing its tail, that we actually think that the microscopically small is very directly linked to the macroscopically large. At one time, galaxies were small quantum fluctuations. So something that was really, really tiny, something that was smaller than a proton, got stretched by the inflation and by the subsequent expansion of the universe by more than 100 orders of magnitude, and it became something as large as a galaxy or a cluster of galaxies. But it's the most beautiful microscope because it preserves that information even though it turns it eventually into a galaxy. And so we think that what goes on in high-energy physics collisions and what goes on in the creation of galaxies and clusters of galaxies is very intimately related. And we didn't know that before, but we do know that now. And so by mapping this very early universe, we've been able to learn that there were these variations, these quantum fluctuations, and we've been able to map out how they may grow over time to become galaxies. And now we're going back and mapping them more precisely. So I got the Nobel Prize for using the Cosmic Background Explorer satellite to make a pretty coarse map. Basically, we would discover all the major continents and all the really big features. Then the next, that was followed by the WMAP satellite, which is more high resolution. And now a year ago, we launched, in May of 2009, we launched the Planck satellite. It's been taking data for a little over a year now. And I have pictures of maps to show, which I hope you guys have received. And I don't know whether you have them at CERN or whether they're at Frascati. But we have these beautiful maps of the sky that we've made in very much higher resolution than we had before, and many more wavelengths. And they show beautifully the beginning of the universe, but they show a lot of detail about our own galaxy and some nearby galaxies. And so we're refining our observations and our measurements very much, but we think eventually what we see in the sky and what we see at an accelerator like CERN, they have to tie together very, very tightly. They have to interlock like this so that we truly know that we understand what's going on.
Okay, George, just to summarize that, what you're actually saying is that something that happened nearly 14 billion years ago, we can still detect the light?
That's correct. The universe is quite large, so we can look out only as far as light can have traveled to us. And so when we look to see the light as farther away as we can see it, it's been traveling to us for almost 14 billion years. And then we wait another year, we'll see 14 billion plus 1 years and so on. And that's as far as we can see. We look back to the time when the universe is opaque, but we look back to a time which is very shortly after the Big Bang. So that light fills the universe and it's coming to us from all directions. And we can see further and further as more time goes on. But given the amount of time we've been observing, which is only a couple of decades, essentially that's a tiny spot on the surface of the Earth. It's like looking at the surface of the sun and only varying around by a centimeter. We're just looking, even 20 light years is small when you look at the surface of the universe.
But George, when I look into the sky, I don't see this light.
You don't see it because the universe has expanded, and it's expanded by a factor of 1,000 since that time the light left. So that light that was visible has now been stretched first in the infrared, then to the far infrared, and then into the millimeters. And if we wait longer, it'll eventually become into the microwaves, like your microwave oven. So we're seeing it now where it's sort of between the far infrared and the microwaves. And that's just because the universe is expanding and stretching the light out. But if your eyes were sensitive, you would see it. But you know, just like you can't see the infrared unless you're a pit viper or something, just human eyes are made to work in the daylight, so they can see the light from the sun where it's strong very well. But you can build instruments that are radio receivers or sensitive thermometers that can measure the heat that's coming in and measure it very precisely. And that's what we do. Then we translate it into maps we can see with our own eyes.
So you started with Kobe, then you went on to WMAP, and now you have Planck. What do you think Planck is going to discover that's new?
My first expectation is the most important thing it does is make a really careful measurement of the sky with much more precision.
Chiedo intanto a Roberto, intanto che ci arriva. Ecco, professor. Good evening.
I recognize this voice.
Our moment of having you all to ourselves is gone.
You're still speaking with, are you still speaking with CERN, I guess?
Yes, that's right.
Yes,
hello,
but now
Paula.
I'm speaking to you too.
Hi, I can see Professor Smoot, who is in Paris, and we are in Frascati, and you're in CERN, Kate. But we would like to be alone with him. Without you, CERN. Just Frascati, please.
You're stealing him.
Okay.
Okay.
That's fine by us. We've talked to George. Before you take him, Paula, we'd just like to say a big thank you, George, for joining us tonight. Thank you to the people in the Paris, okay? So we leave you.
It's my pleasure, and I wish CERN a lot of luck, because I want you guys to discover great things, so we'll really understand the universe. I want to see great leaps in the next few years.
And remember,
So do we.
Paris is not very far from Geneva, so please hop over.
Exactly.
So can I speak now?
Yeah,
Yes,
Paula,
go.
enjoy.
Okay, do we cut Paris now, Silvana?
Yes, we do.
Okay, but luckily, as we have another guest who sneaked onto the stage without you seeing him. It's Alvaro de Rujula, CERN theoretical physicist, who has come along to talk to us this evening. I've got a question for you, Alvaro, to kick things off on this field. I've often wondered, how on earth do we know that the universe is 13.7 billion years old?
Because the universe is currently expanding, and we know how it's moving. So we just play the video backwards, so to speak. It's like a balloon which is inflated. So you play this video of the inflating balloon backwards, and you go to the point where it began. And we have a very good description of the details of the universe, and we can figure out that it is 13.7 billion years old with quite some precision.
And what do you think about the impact of Kolbe, WMAP, and Planck? What have they brought to our understanding of the universe?
They have added a much better knowledge of how things evolved till today, from an original soup that was almost uniform. And they have also brought, as usual when you understand something new, you find another problem which you don't understand, which is even worse.
And what's that?
And the problem that they found, which is even worse, is that the universe is accelerating. And in order for it to be expanding, it's enough that it just began with a certain motion. In order to be accelerating, there must be something acting on it which makes it accelerate. And our current ideas about what that is actually date back to Einstein, and they are, in the modern point of view, the energy of the vacuum. If you take a room like this room and ask everybody to leave, and then you take the lights off, and then you cool it to absolute zero temperature, and then you take all the air out, what you made is a vacuum. Now it turns out that the vacuum is not empty. It has something that you cannot take away from it, which is something like an energy density. And we think that is this energy density of the vacuum that is gravitationally acting as a negative gravitational force from one point to the other, and that's why the universe is expanding. The vacuum is the simplest of all things, and it's also the most mysterious.
So that's what we call dark energy.
That's what we call dark energy.
Is the
the question of dark energy is not clear.
Is the LHC going to shed any light on dark energy?
It's conceivable, although nobody has a connection which is obvious. But the fundamental problem about the smallest things, which are the elementary particles, and the fundamental problem about the biggest thing, which is the universe, is the same. And the problem is again the vacuum. We think that when a particle moves in the vacuum, it sees the vacuum somehow, and the mass of the particle is the friction, quote unquote, between the particle and the vacuum. We do not understand the origin of the masses of the particles, but we think this is it. That the vacuum is not only responsible for the acceleration of the universe, but also for the masses of the particles that compose it.
There's something else that's dark in the universe.
There's something else which is dark in the universe, which is called the dark mass. We have so many dark things in the universe. We are not dark, at least I am reflecting light, and that's why you see me. And the material of which we are made, which is called ordinary matter, of which the stars are also made, and the planets, and the galaxies, is called, this ordinary matter is only about 4% of the universe. 20% is something called dark matter, which we don't know what it is, and 70% is the dark energy. So this is the biggest revolution ever. We're not only not the center of the solar system, we are not even made of the things that the universe is dominantly made of. We are really some kind of little extra salt in the universe, in the soup that constitutes the universe. We are a minority.
So if this matter is dark and we can't see it, how do we know it's there?
Because we see it, although we cannot see it. And one of the ways we see it is the following. You look at very distant galaxies, which in between the position where they are and you, there is another ensemble of galaxies called a cluster of galaxies. Now, the mass of these galaxies deflects the light when it comes to you. If you see a star very close to the sun, it is not quite where you think, because the light comes around the sun bending. So when you look at these galaxies that are behind other galaxies, the light from these galaxies is bent in a specific fashion that tells us how much mass there is in between you and the observed galaxy. It turns out to be much more, like 5–10 times more, than the visible mass. You see the visible mass of the galaxies, but the galaxies also have dark mass, which you do not see directly, but you see indirectly because it acts like a lens. And you know how the lens is made because you understand the picture very well. And it turns out that it is a few times more massive than the matter that you see. So we know, because of these observations directly, that there is dark mass, and also the observations about which George Smoot talked about also give us this number. 20% of the matter of the universe, of the energy density of the universe, is in a substance called dark matter, which we also don't know what it is. And before you ask me the next question that you are going to ask me, the answer is yes. We are also looking for the constituents of this dark matter at the LHC.
How did you guess?
I was just about to ask.
It was relatively easy, and the LHC is only 50 meters under us, right here.
So we are going to potentially give some clues as to what dark matter might be at the LHC.
Potentially is the right word, because we physicists cannot promise anything except that we're looking for something, but we cannot promise that we're going to find it. That kind of promise is left to the politicians.
Okay. I was making a video conference earlier this evening with Serbia, Novi Sad in Serbia, also for this night of researchers, and a lady at the back of the room asked me, or asked the Serbian physicist who was with me, what use would it be? And she was relating to something else, but I'll repeat her question to you. If we discovered what dark matter was, would it be any use to us?
More or less like the music of Bach. Is it of any use to you?
Okay. Okay, I'll let you work out the answer to that question. Is there anybody in the audience who would like to ask Alvaro a question about cosmology or astroparticles?
Perhaps there was a question you were dying to ask George Smoot, and we can direct it now at Alvaro.
Yes.
Yes, one here.
Hello.
George is no longer online?
I have a question for you. How can you be sure about knowing when you make this estimation of the dark matter from what you were saying about the visible matter, how can you be sure of the measurements of the visible matter, considering that the galaxy is very, very far away, and I don't know if one star is behind the other?
We have so much evidence for that, even in our own galaxy. You see, if you look at gas orbiting very far away around our galaxy, it doesn't orbit as if the mass of the galaxy was what you see. It orbits as if the mass of the galaxy was 5 times what you see. So even in our own galaxy, even here where you're sitting, there is a certain density of dark matter. You're being crossed by particles of dark matter all the time. So on the dark matter, we have 5 or 6, maybe not, 3 or 4 pieces of independent evidence which are all in very good agreement with each other. So that is undoubtful. Yeah.
Okay.
We've got a question on the internet.
Okay.
So, is CERN involved in astrophysics research, and do they have their own telescope?
Could you tell us where the question comes from?
Caroline from Paris, France.
Okay, Caroline from Paris, France. Could you repeat the question?
Yep. Is CERN involved in astrophysics research, and do they have their own telescope?
Okay.
Yes, we have the most peculiar telescope in the world, which is looking at another type of hypothetical particle from the sun, which is called the axion. It's something that we wish existed, and for very good reasons. And the sun, if these particles exist, is emitting them. And the way we are looking at them is with a magnet from the LHC, which looks at the sun for a part of the day. It's moving like this, following the sun. And if axions come into this magnet, they will be converted into light and seen by a camera at the end of the magnet. So it's a telescope, but it's actually a magnet. It's the only telescope, I think, which is a magnet. So yes, we have the most peculiar telescope anywhere.
And we can just insert a little bit of publicity here for CERN. Of course, you can come and visit. If you're out there on the internet, you can come and visit CERN. We have 50,000 visitors every year. And one of the experimental facilities that we take people to see is actually the CAST experiment. Another question, Sophie?
So we have a new type of neutrinos apparently recently been discovered. Yeah, a new type of neutrinos been recently discovered. What does that change in physics? And it's from James in London.
James in London. Thank you, James.
You said that new types of neutrinos have been discovered. That's not quite precise. What has been discovered is a property that neutrinos might or might not have had, which is mass. What has been discovered is that neutrinos are not massless, like the particles of light, which are also neutral, like the neutrinos, but have a tiny, tiny mass and mass difference between the different types of neutrinos. So we have learned more about some of the fundamental particles, which are these neutrinos. And we think that this has connections with all sorts of other things, like what happens at physics at very, very high energy, which will be involved in the production of neutrinos, in the masses of neutrinos. And we also think that there is a connection between this new property of neutrinos and the way in which the universe developed more matter than antimatter. If the universe had had, as any decent person would think, the same amount of matter and antimatter, the two substances would have annihilated and become just light, and we wouldn't be here. And there is a connection, possible connection, between the fact that the neutrinos have no mass and the fact that we are here.
Okay, thank you. I'm being told that we're going to play you the clip that I announced earlier. It's a clip about an interview with a guy called Raimundo Lazy, who works on the Planck experiment, who's actually a collaborator of George Smoot.
We are now in Bologna at the National Institute for Astrophysics in Italy, and we are with Professor Raimundo Lazy, principal investigator of one of the two instruments aboard Planck. So, Professor Raimundo Lazy, this Planck satellite, which are its main scientific goals?
The main scientific goals of Planck with the third generation mission of the European Space Agency after the two NASA missions, COBE and WMAP. The main goals are the understanding the present knowledge of our universe and determine the major characteristics which will give us information on the really first instance of its birth, like the quantum fluctuations which give rise to the present structures within the universe, like the possibility of determining and detecting the primordial gravitational waves, like understanding the origin of the dark matter and the dark energy.
Very ambitious achievement, those of Planck, but how can it collect the most ancient radiation of the universe? Can you tell us some secrets of the satellite?
There are no secrets. I mean, certainly Planck, the satellite is it's a very complex satellite with a lot of technical innovations. It's essentially a 1.5 meter scale telescope with two instruments on the focal plane. One is the low frequency instrument whose PI is myself, and the 2D construction of the instrument which is based on radiometers, radio receivers, which are observing the first light of the universe, the cosmic microwave background, from 30 to 70 gigahertz. And there is another instrument which is based on barometers, like thermometers, which are cooled at 0.1 Kelvin. It's only 1.1 Kelvin above the absolute zero temperature. And the leader of this instrument is George Smoot from the Institute of Space Astrophysics in France, at Frascati.
Planck has now been flying for 1 year and a half. What is going to give us in the next few years?
I think today is the 501 day of observational days of Planck. The data are sent to the two data processing centers in Trieste and in Paris. And from a very careful analysis of the data, we hope to get out information concerning the instance after the birth of the universe. That is what happened during the inflation. We would like to understand if we can detect the primordial gravitational waves, and say something and say more than something on the dark energy and dark matter. After the end of the Planck mission, what I believe the future will be in Euclid, which is an ESA mission, which aim is to study the evolution of the universe from the time of the first light emission to now, and the main purpose is to study the so-called dark energy in much more details that will be done by Planck.
Okay, thank you for the clip. I noticed while the clip was running that Alvaro was playing around underneath the table, and it looks as though, although he's a theoretical physicist, he's brought some experimental equipment with him. What on earth is it, Alvaro?
Well, just in case it was required by the questions, I brought my pocket universe here. The question is how physicists understand the notion of the expansion of the universe. It's a very difficult notion because it's the space between things that is expanding. And it's not everything that is expanding, it's just the space between things such as us and our galaxy and other distant galaxies. So it is as if everything that existed was like the surface of this object or the surface of the Earth. the third dimension, inwards and outwards, for this demonstration doesn't exist. So suppose that space had only two dimensions. Suppose that space had only two dimensions, and that something was inflating them like this. So you have someone here and someone here, and they think they are separating from each other because the space between them is stretching. And if someone is twice as far, this shadow person would have the impression that it's moving away from this one at twice the speed.
I can hold it for you.
And yeah, this is going to be so difficult now. You see this law that something which is twice as far is moving twice as fast, apparently, although it isn't moving, it's just stuck here, like a little animal that would be here, like an ant. Even if the ant isn't moving, this ant here has the impression that this ant here is going away because the space between them is what is being inflated.
I'm getting a bit worried here, Alvaro.
Now,
if you keep pumping.
Why do we think that the universe had a time in which it started? I talked about that before. It's because we can run the video backwards and look at the time when it all began, when this was roughly a point.
But Alvaro, I have a question. How far does the analogy go? If you kept pumping that balloon, it would burst. That's not going to happen to us, is it? You've got me worried.
It won't bother you. You see, the universe, we cannot predict to the infinite future because our measurements are not infinitely precise. But we can predict very far in the future of the universe to some time when it'll be 100 or 1,000 times more stretched than it is now. So the universe is going to expand, we know this observationally, for a long, long, long time, like 1,000 or million times its current age. Okay, so now what will be the only important consequence of that will be that the other galaxies will be so far away from ours that we won't see them. So the field of astronomy will die away because we won't see the sky, only close by but not very far away. So the cosmologists will have to become something else.
So is this a plug for particle physics then?
Probably. Does anybody have a question for Alvaro about this interesting demonstration that he's done? Yes.
I find it difficult to, well, I wrestle with the notion of the two-dimensional expansion when everything about us is three-dimensional.
No, you think that it is difficult to understand, but you understand it perfectly. Suppose instead of 2 dimensions, I only took 1 dimension. So I take an object which starts here. The object starts on my left hand and continues over there. Now, suppose it is stretching. 1 point and another point will be further and further away. This is quite understandable in 1 dimension. Now I showed to you in 2 dimensions, which is the surface of a balloon. The reason why you have difficulty understanding it in 3 dimensions is that your mind is not used to thinking 4 dimensions. If I could blow the balloon in 3 dimensions in a space that had 4 dimensions, then you would understand it perfectly. But you understand it for 1 dimension, you understand it for 2 dimensions, please understand it for 3 dimensions. And for a mathematician or someone trained in this kind of thing, it's not a difficulty. Because the equations are simple independently of the number of dimensions, and they are the same.
Alvaro, theoretical physicists like yourselves talk about more than 3 spatial dimensions. Where does this come from?
It comes from the idea that every point in this space, which we all know has 3 dimensions, if you ask a Chinese person in China to steal an apple, you have to give 3 instructions. which direction, how far, and how high in the tree. And this is also true for a French thief. Independent of the language and everything, the fact that there are 3 space dimensions is a truth that we can all check. However, it is possible that every point in these 3 dimensions in this room is not quite a point, but it's itself a kind of little ball with internal dimensions. And we have reasons to think that this is quite conceivable. And the answer to your question is yes.
I knew you were going to say that.
We are looking for this at the LHC as well. We are trying to figure out whether at the energies that we can reach with this machine, which are presumably not sufficient, but we try, we can figure out that space has internal dimensions. That is to say, each point is a little kind of sphere.
And how would these show up at the LHC?
How this shows up because if each point, let me not make it a sphere, let me make it a cylinder, okay? And this is because I have a cylinder here. If you wrap around this cylinder a string, it will have a certain property, a certain mass in particular. If you wrap it twice, then it'll have exactly twice the mass. If you wrap it 3 times, then it'll have exactly 3 times the mass. So if we find a series of particles whose masses are like this, the mass of the first is 1/2 of the mass of the second, is 1/3 of the mass of the third, etc. Then we have a very good hint that something like what I said is correct.
Okay. Yes, we have a question.
Following on your thought of many dimensions, would you care to give your own thought on the M theory, which has recently been the object of quite a bit of press?
The M3?
The M theory of Stephen Hawking's.
Oh, the M theory has nothing to do with Steve Hawking. This is my first comment on the subject. He may have talked about it, but the book I haven't read. I'm not planning to read it anyway. And the M theory is a generalization of what is called string theories. String theories are theories in which, contrary to the observation so far, the elementary particles would not act as points, but would act as strings. I have already talked about a string for a moment, putting it around my thing. It's a similar kind of string. And it would be, if this theory is correct, only 1 or 2 types of strings whose different vibrations, like the different vibrations of a string in a piano, you have the fundamental one and the next one, etc. Those different vibrations will be the different particles. So it will be a very economic theory of particles. It's also the only theory in which we can unify convincingly the force of gravity with the other forces of nature. So it's a very attractive theory. The only problem that it has is that it doesn't have, at the moment, any prediction which can be proved wrong. And that's what happens in science. You go towards the truth by proving other things wrong. This one cannot even be proved wrong at the moment, so it's in a sense not a theory of physics.
Okay, Alvaro, thank you very much. I think this is the time we have to say a big thank you to Alvaro for coming and talking to us about this subject. It's a fascinating subject. I know that he can talk about it for a long time, but we're going to move on. Please stay with us, Alvaro. Let's give him a big round of applause. Thank you.
Thank you.
And we're going